So, Bobby, we talked about search coils.
Oh, fluxgate.
Yes. So, thought, let's...
I know flux and I know gate. But what is flux?
And you know what a magnetometer is,
Right? Or some idea, yeah,
right? We've done a lot of work on search coils. Let's look at another magnetic sensor called fluxgate.
Yeah.
Magnetometer.
I remember you saying this can be used to measure some nanotesla magnetic field with the picotesla resolution, etc.
Yes. So a very sensitive magnetic sensor.
Yeah.
Fluxgate.
And picotesla resolution is something.
That's very good, right?
Yeah.
Very sensitive. Yeah, resolution is very good. But what do you see here? I mean, to me, it's like a search coil with the core, right?
Excitation.
I mean, I see two coils.
Yeah.
As you said, excitation coil. I see a pickup coil. So see a paramagnetic rod. I mean,
correct.
What's going on? I mean, are we doing this? This looks like a search coil to me.
Yeah.
Do you see any kind of difference within the structure of the coil or the design?
For me, at the moment, looks same.
It's the same, right? I mean, excitation coil, pickup coil, a ferromagnetic rod that has, let's say, some hypermagnetic permeability.
Correct.
And
what is the one nearby? Why you are using two?
Oh, no. So, you mean these two?
Huh?
We'll talk about it a bit later. But yes, that's the first clue. That's the first clue.
Okay.
To the difference between a surge coil and a fluxgate. But when you first look at it, it looks like it's kind of the same design, right?
Yeah.
But what else do you see here?
We are also saying earlier, surge coil means just a coil alone.
But we also had the surge coil with the core. Later on,
surge coil with core was there.
Yes.
But I've not seen an excitation coil and a detector coil kind of.
Pickup coil, yeah. They were not separate.
Yeah.
I mean, we talked about a situation where the one coil was used for both the excitation and pickup, like eddy currents.
Yeah.
But of course, in surge coils, some probes have a separate pickup coil too. But you also have here an AC excitation waveform. Okay. And a voltage output. Again, very similar, right?
Correct.
So it's increasingly looking like a surge coil setup.
Yeah.
But you asked me what's the difference between this and this.
Yeah.
So what you see here are magnetic field lines.
Correct.
Okay.
But why one is like this and one is straight like that?
So one is somehow concentrating at this core, and here it's going straight.
So the second one also has a core, or?
Yes, both have cores. The design is the same.
Okay.
But in one, it's converging and concentrating at the core, and here, it's going straight through.
Oh, what did you do to achieve this?
Exactly. Why do you think there's a magnetic field that is concentrating here, and then all of a sudden, it's not anymore? What could be the reason for that?
Earlier, you mentioned about something called demagnetization.
Yes.
Whether it has something to do with that? No, because it's both are same shape only.
Both are same shape.
That has something to do with the shape of the object.
Yes. Demagnetization is, something to do with the shape of the object. But demagnetization is part of something, is part of what we call the magnetic
permeability. Correct.
Right?
Correct. It's not that.
No? It's not the permeability?
Yeah. That it was part of permeability, I remember. Yes. I forgot the exact term.
Yeah. It's part of permeability.
Yes. I remember it was mu r by some nd into.
Yes. And then we also talked about if you keep on increasing
what?
The applied magnetic field,
it will get saturated.
It will get saturated.
That's true.
And then what happens when it's saturated?
Okay. So the mu r
mu r or mu dash or mu r, whatever you call it.
Will reduce because it is saturated. Yes, I mean you are increasing H, but it's not B is not increasing.
Yes.
So B is equal to mu H.
Once it's saturated.
It's
Like air.
it will be like air.
Yeah.
Oh, so the second one is saturated.
Second one is saturated.
Okay.
So that forms the basis for fluxgate magnetometers. But let's talk a little bit more.
So that means for the second one you have applied more excitation.
Yes. So for the second one, you are increasing the applied magnetic field. So of course, at a certain stage, it will saturate, and the fields will not be able to induce any extra magnetic.
Because it's also like air. Is air, right? Got it.
Now I'm sure you've seen the
Hysteresis loop.
Yes.
Right. The ferromagnetic material.
Yes, I think this is probably one of the most commonly recognized symbols of magnetism, right? And one of the most frequently tested characteristics of magnetic materials. So if you get a magnetic material, ideally, if you want to look at the characteristics of that magnetic material, this is one of the most common tests we use to do that.
So here, how will you get this characteristic? Initially we are assuming there is no H.
Yes.
So you are at the center, 0, 0.
Here.
And then if I keep increasing H, I will go through that dotted line.
Yeah. So imagine you have let's say a soft ferromagnetic material. It's either demagnetized or it's not magnetized.
Let's assume there is no magnet.
Let's assume there's no
magnet.
So then we'll start from here.
Yeah.
Right. Now
it has a coil and you are increasing the current through that.
Exactly.
So that means you are increasing the H.
Yes.
H is some Ni by L.
Yes.
Correct?
Yes. So now you are increasing the
I or H.
Yeah, I or H, right? This way.
So at some point, you will reach the saturation.
It's just saturation. Yeah. Okay. So you reach the saturation, fine.
Now I reduce the current.
Yes. Now you are going this way. Now you are going this way. Right? Now you're reducing the magnetic field.
But it's not, the B is not coming back through the dotted line.
Yes, because now
a different route.
Exactly. Now you're now applying a zero field.
Yeah.
But you have
some field in that material.
And this is what we call remanence or remnant.
Yeah. Or residual magnetic.
Or residual magnetic.
Magnetic field
or something like this.
Or this property is residual magnetism.
Yes.
The value remaining is the remanent.
Remanence. Yeah. Remanent field or remanence. Yes. But what happens now?
Now you want to bring it back to zero.
Yes.
So that means you have changed the direction of the current.
Exactly.
Okay.
Which means now you have a negative magnetic field, right? And at a certain point, eventually, finally, it will
reach zero.
Now that value is called coercivity.
Or the force that you have applied, the magnetic intensity that you applied to bring the B from residual magnetic field to zero.
Yes, because in English, coercivity means you're coercing someone against their wishes.
Yeah.
That's what we're doing here, right? We are saying, hey, you're not zero, to coercing you to come back here, right? So this field is called the coercive.
Yeah.
You need to add something extra in the other direction to bring it back to zero.
Yeah.
Now what happens? Now if you keep increasing your magnetic field in the opposite direction.
I will go to the negative saturation.
Then you go to a
negative saturation.
And then you increase again. Again, you have E
then
here.
We are decreasing the current.
You're decreasing the current, right?
So you will come back in this fashion.
But then again, it will not go to zero at zero.
It will go to its remanent field.
And
then you flip the current in the positive direction and increase. You will go back to zero. And then the story continues. Yes. That is how you get this loop.
Yes. And this is called the hysteresis loop. Now, for each cycle, you reach saturation twice. Right? Yeah. One in this direction, one in this direction.
Yes.
And these two fields are generally equal. And these two is also generally, ideally, equal. Okay, but then what does this have to do with this?
So if I apply H beyond that saturation,
Mhm.
then I get that second figure. That's what you said.
Yes, exactly. So once you're going up, once you're going here, increasing, then you will have
Like that.
the flux density
Yes.
converging.
Yes.
Once you reach here, you get this point. Right?
Got
This is saturated. Got it. And again, if you go in this direction, same thing, right? You come back here and then go back here. So this is the principle we use when designing and operating fluxgate magnetometers. But then how exactly do we use this? Right? For a start, why would you use a soft ferromagnet? I mean, I guess the students know the difference between a soft and hard ferromagnet. I'm not sure. Why would you use a soft ferromagnet in this case? For your core.
What is the main difference between soft and hard? The hysteresis loop size will be different.
Exactly. So you have a lower coercive field and lower retentivity, right? Or you get a skinnier for a soft ferromagnet.
The other one, it will be big.
Yes.
The area of the hysteresis loop is also giving some information. No? There is something called hysteresis loss.
Yes.
Correct. So if hard magnetic material, I think the losses are also slightly more. So the loop size will be
bigger. Yes. So you rather have something like this there.
Yeah.
Correct. Under like this. Correct. Now, ideally, okay. But then again, my question is, okay, fine. But how is that related to this flux gate?
Or the question is, how can I measure the small value of magnetic field knowing this much?
Yes.
Correct. So if there is some excitation to the core and it's already at some point in the hysteresis loop, if there is an external magnetic field, let's say a DC magnetic field, yes, it may drive slightly into saturation or move downwards. I mean, depending on the direction of the magnetic field.
Correct.
Depending on the, let's say, H is the one produced by the excitation coil.
Yes.
Let's say HX is the one we want to measure.
Yes.
So due to HX, I may drive towards saturation or away from saturation.
Yes. Correct. That's right. So
also another thing, I think when it is in saturation, the
pickup current,
the voltage that you are measuring will go to zero.
Yes.
Because there is no rate of change in the magnetic field.
Yes.
Correct.
So there will be a sudden drop.
Yeah.
You might see something and there will be a sudden drop. So, okay, let's.
So if I apply, for example, a triangular waveform as the excitation signal, right? Right?
Yes.
And then if I try to look at the induced voltage in the sensing coil or what's the coil? Pickup coil.
Right?
How will it be?
Well, Bobby,
you have that.
I have the graph exactly here.
Okay.
Right? Now, you talked about why did you pick a triangular coil?
Because triangle, it's with respect to time, it's linearly increasing.
Okay.
So it may be easy to analyze.
Understand, yeah. So now this is the magnetic field we were talking about before.
Yeah.
Right?
So this is with respect to time.
This is with respect to time. Right?
So you have current or H as a triangular waveform.
Yes. Which is applied by this excitation coil, right? Then what happens? This is increasing.
That is the
applied field. Applied field. And then what's going to happen to your magnetic flux?
Bombay. So until saturation, the field will increase almost linearly with respect to H.
Yes, but at some point, I mean, this could go to a maximum, but before that, your B might
reach the saturation.
So
B stop there.
Yeah, which is what you see here.
Yeah. Then when you are coming back after the residual
which is this way.
Yeah.
then we will at some point,
After this,
at some point,
correct.
This will also start coming down.
Yeah.
Okay.
Yeah.
And
So the one moment, sorry, the hysteresis loop that we are assuming here is almost like a square shape for this drawing. I mean, here, here it's the hysteresis loop is almost like a square shape. Like,
yeah. In this case,
Yeah.
yes, correct. For this triangle wave,
correct.
So then, obviously, if you go the other way, it's the same thing.
Yes.
Right?
Yeah.
It will go to saturation.
Yeah.
It will come out of saturation once this goes past a certain
Yes.
value.
Yes.
Now, what are we measuring here, though? We're measuring the change in the magnetic
Field.
or the flux density, or whatever it is, right? So here you can see
Core.
in the core.
So in the core is changing only in that period.
Exactly. So which means you have a high value here,
So you have a dB by dt.
which is what you have here, right? And this is the highest when this gradient is the highest.
Yeah.
Now, what happens when it goes to saturation?
No gradient.
No gradient.
Zero
So,
volt.
comes down to 0.
Yeah.
And it will stay 0 until,
There is a change in B,
which you see here.
which is in the negative direction.
Correct. And then it will go in the opposite direction.
So you get pulses like this
When you drive,
into saturation and coming back.
exactly.
Got it.
Which is what you do with this excitation waveform. Now, what happens?
If there is some HX or
Exactly. What happens?
there is some external magnet.
External magnetic field.
So it may drive, depending on the direction of the HX, the external magnetic field, right? We may drive early into saturation.
Exactly. Which is what you see here. Right? So here,
Yeah.
now it's kind of shifted this way.
Yeah.
Right? So it's now going into saturation.
So the core is seeing now H plus HX.
Yes. So imagine now, imagine it's a DC field.
Correct.
Okay?
Correct.
Our applied magnetic field is a
Triangle.
triangular waveform, but what you're trying to sense, so don't confuse this magnetic field with the external magnetic field, right? Because now, before here, H, you have H, let's say H total is H
Plus HX.
H plus HX.
And HX we are saying it's a DC magnetic.
Yes. So let's say here it's H is H,
Oh.
but now the total is H plus, let's say H EXT external.
Yeah.
Right? And this is a DC.
H external is the one you want to measure.
Yes, this is what we want to measure.
Okay.
And this is what we are applying here, the triangular waveform.
Yeah.
Through your primary coil, your excitation coil.
So for the core, it is like an H waveform with a DC offset.
Yes, which is, we see like a little bit of offset there.
Got it.
Now, let's say now, this DC field is a DC field, so it's one direction or the other. Let's say it's in this direction.
Yeah.
Now, let's say initially, your coil is going up and down.
Yeah.
But you'll have one part of the coil that is exposed to this DC field. Not one part of the coil, but when you're going through the BH curve, right? If you're going, let's say, a positive field,
Yeah.
right? Then that will be in the same direction as this field.
Yeah.
So you go to saturation quicker.
Yeah.
Right? Because now you have an extra magnetic field in that same direction. So you go to saturation faster. And when you, so I'm talking about this field here, right? Now, when you reverse the applied magnetic field, what's going to happen? You still have this extra magnetic field. So it's going to stay longer in saturation.
Yeah.
So you need a larger magnetic field this way to reverse that.
So essentially, you are in the saturation in more time compared to no external magnetic field.
Assuming that the applied field and the external field are in the same direction.
Yeah. Correct? Yes.
Now what happens?
Otherwise, it will be opposite. In the sense, you will be in less time in saturation.
Yes. So otherwise means now, because this is the AC waveform and this is the DC waveform, here, now you're going in the other direction, but your DC field is in the opposite direction. So what happens is you stay a shorter time in saturation because you have an opposite field, right? So and that's what you see here. But then what happens to dB over dt? That's the interesting part.
dB by dt will be same again.
dB by dt will be same, but what do you see here though?
That flat region,
Let's
where
say the
there is
time.
no output,
Exactly. See, it's the time.
duration will change for the positive waveform
Exactly.
and negative waveform.
So what that means is, there will be some phase difference, no, between.
If you compare with no external magnet.
Exactly. If you compare with no external magnetic field, compare that with an external magnetic field that you're trying to measure, you will see some phase shift here.
Yeah.
Now that phase shift, or the value of that phase shift, will be related
Has
to that information about the
external magnet.
magnetic field. So that's the basic of a fluxgate magnetometer. Now, but there's another thing I want to talk about. So for a search coil, right, we had what? V minus d phi dt, right, which is equal to minus dB over dt times Na. Okay. Now, if you sub your usual B equals mu 0 mu r h, right, then you get what? Minus d over dt, right, N A mu 0 mu r h, correct? Okay, then which is equal to mu 0 n minus, here inside you have mu r a dh over dt plus mu r h dA over dt plus a h d mu r over dt, right? Now there are three possible contributions.
So what are these? Mu r a dh by dt. Mu r a mu r h dA by dt. What is a? Area of the
the cross sectional area here of the pole. Okay, right?
And a h, so mu r by dt.
Okay. Yes.
So all these variables can change.
Now, but the first one, you know the first one.
Yeah.
First one you probably recognize as the output of a search coil.
Yes.
Okay. What about the second term? Second term says your cross-sectional area changes. Now,
but the coil area we are not changing.
We are not changing. Unless, let's say, your core, the dimensions of your core, let's say, somehow changes due to, I don't know, something like magnetostruttion or something. Yeah. But no. So we can ignore that.
Yeah.
Right? Yeah. So what are we really looking at? You saw the graphs before, right? But we talk about saturation. So what do we, when you talk about a flux gate, what are you really focusing on? You're focusing on this one, right?
Yeah.
Which is the change of your permeability over time. So that's one of probably the major difference between a search coil and this. But you...
we have output due to both.
Exactly, yeah, exactly. But we will also have this pickup coil in our output. So, and that's something...
But that, you are not interested about that?
No.
Are you interested or?
No, I'm not interested. I just care about this. So later on, we can probably see that this is actually disadvantage because we don't really need that output, right?
So you want to somehow remove that?
Somehow get rid of that. But this is probably the main difference between a search coil from an equation point of view. Got it, right? Now, but there's more. When you're designing a real sensor, what did you talk about in the first slide? I said, oh, what's the difference between this? You said what? I asked you, what's the difference between these two things? You said, oh, yeah, it's the demagnetized correct effect, right?
Yeah.
That is also something we need to consider because when you're designing a real coil, that is, you have your apparent, we call it the apparent permeability, mu r, divided by mu r, I think plus, I think it's got 1 in the, ND is your demagnetizing factor, we said. 1 plus, I think, or rather mu r plus 1 same. Mu r dash, mu r plus 1. Yeah. So this value should also be considered here. So that means your demagnetizing factor of your coil also plays a part.
But it may be a secondary effect.
It is, yes. But when you're designing something, that means your output will also reduce according to that factor.
Correct.
Okay. So let's see next. So we talked about that.
I have a question.
Yes.
Now you have this output, no? The previous slide.
Maybe this one.
Okay,
Here.
this one.
Yes.
Now suppose if I have another, you had 2 there.
Yes.
In the initial diagram.
Yes.
So I mean you had 2 cores there.
Yes.
Although they were shown for
Different situations.
Yeah. Now let's say the second one I am exciting in the opposite direction at the same time. Okay. What will happen?
You're getting ahead of yourself, Bobby. You're too smart for me. Are you trying to get rid of this? You're trying to get rid of this.
Yeah.
You don't like this, huh? You don't like this output that we get when there's no magnetic field.
Correct.
Good point. That is exactly what we will talk about next.
Okay.
So one thing I forgot to mention about the surge coil and the flux gate, because it looks very the same. So now we understand we are actually focusing on this rather than this. And now you said, how can we get rid of this? And you now given a solution. Okay. But another thing is, in surge coils, we talked about measuring a change in magnetic field.
Correct.
But here, according to this equation, you can also measure DC fields.
Yes.
Right? We don't, doesn't necessarily have to be a change in magnetic field to use this.
Yeah. Right. In fact, the external that you're shown,
Yes.
is at a very low frequency compared to the frequency of triangular waveform.
Correct. Yes. So that's another thing that the students should not confuse, right? So this, maybe it's better to show this one. So this frequency, right? Let's call it F excitation.
Yeah.
Okay. And then you have this HEXT.
Yeah.
Okay. We assumed it's a DC field, but let's say it's a low frequency magnetic field, or magnetic flux or whatever. This frequency
should be very, very low compared to FX excitation.
This should be EXC,
Yeah.
EXT. Yes, exactly. Very good point. So this frequency must be at least
maybe one order.
Or
a couple of orders.
I mean, according to Nyquist, this should be twice. But I think generally when you're designing this, this is probably much, much higher than what you're trying to measure.
Yeah.
Correct. Yes. Because then, why? Because when this is much, much higher than this, then you can kind of treat this as a DCC.
Right. As far as that excitation frequency
is concerned.
Yeah. Because during one cycle, this is not changing.
No.
The external field is not changing.
Yes. Got it. Yes. Yeah. Good point.